Hello everyone. So far, we studied the boundary value problems in Cartesian coordinate, x, y, z coordinate. In this chapter, we will study the boundary value problems in other coordinates, such as polar coordinates. So in these chapters, we are going to study the boundary value problems in other coordinate systems. First section is a polar coordinate. Second section is a cylindrical coordinate. Third section is a spherical coordinate. First section is a polar coordinate. To describe the positions of particles, we use the x, y in the Cartesian coordinate. If we use a polar coordinate, we could use the r and theta to describe positions. We could convert from the xy coordinate to the r theta coordinate using these relations x equal r cosine theta, y equal r sine theta. If you know the xy coordinate, we could derive the r and theta, r square equal x square plus y squared, and tangent theta is equal to the y over x. So from these equations, we could find the partial derivative of r with respect to x, because r is expressed as square root x squared plus y squared. So take a partial derivative of r with respect to x. So it becomes 1 over 2 square root x squared plus y squared. And you apply the chain rule. Partial derivative of x squared plus y squared with respect to x produces 2x. So it becomes x over r. So this is equal to the cosine theta, because the x is equal to the r cosine theta. So we derive the first equations. Also, we can find the partial derivative of r with respect to y. Same with y over r. It becomes a sine theta. So we derive the second equation. Now we'd like to derive the equation for the partial derivative of theta with respect to x. To derive this equation, we use a tangent theta equal y over x. Tangent theta equal y over x. Partial derivative with respect to x in the both sides of the equations. So from this equation, derivative of the tangent theta with respect to theta, it becomes 1 over cosine square theta. By chain rule, round theta round x equal minus y over x squared. So from this equations, round theta round x is expressed minus cosine square theta y over x squared. So if you substitute y equal r sine theta, x equal r cosine theta, it becomes minus sine theta over r. Also, you could find out the partial derivative of tangent theta with respect to y. So it becomes 1 over cosine square theta round theta round y equal 1 over x. So from this equation, round theta round y equal cosine square theta 1 over x. If you substitute x equal r cosine theta, it becomes cosine theta over r. So we derive the partial derivative of the theta with respect to x and y. Then we'd like to express the partial derivative of some functions. So as a function, we choose a u. U is a function of the two coordinates. U is a function of x and y. Also, we could say that u is a function of r theta. Then we'd like to convert of the partial derivative of the u with respect to x to the partial derivative of u with respect to r and theta. To derive these relations, we apply the chain rule. So we multiplied round u, round r, round r, round x, round u, round theta, round x. So we derive the round r, round x, round theta, round x. Round r, round x is a cosine theta from this equation. Round theta, round x is equal to the minus sine theta over r. So you can substitute that equations. So this corresponds to the round r, round x. This corresponds to the round theta, round x. Then we derive this equation. Also, we could find the partial derivative with respect to y with the same weights by chain rule. So round r, round y, round theta, round y. We can substitute. So this corresponds to the round r, round y. This corresponds to the round theta, round y. Then we derive the round u, round x, round u, round y. Now we'd like to derive the second partial derivative. Second partial derivative of u with respect to x is expressed this one. Then first partial derivative with respect to x is expressed using the chain rule. Then round r, round x is equal to cosine theta. And round theta, round x is equal to minus sine theta over r. As a round u, round x, we use these equations. This equation substitute into the here and here. Then we could perform the partial derivative. Then little bit complicated equations we obtained. So this is a second partial derivative of u with respect to x. Then we could also calculate the partial derivative of u with respect to y. Again, we apply the chain rule. Round r, round y. Round theta, round y is multiplied. Then round r, round y. This is equal to sine theta. Round theta, round y is equal to cosine theta over r. Then you can substitute first derivative of round u, round y is here. Round u, round y, same terms is here. Then perform the partial derivative with respect to r and partial derivative with respect to theta. Then we obtain these equations. Then by summing up the partial derivative of the u with respect to x and y to find out the Laplacians. Laplacian u is given by the sum of the second partial derivative of u with respect to x and y. So if you substitute the equation is really simplified. So this is the expression for the Laplacians in the polar coordinate. Second derivative of u with respect to r plus 1 over r. First derivative of u with respect to r plus 1 over r squared. Second derivative of u with respect to theta. We obtained expression of the Laplacian in polar coordinate. Then we can express the heat equations and wave equations in polar coordinate. Okay, this is the end of the first session.